I guess we'll go ahead and get started. So Avishal, if you'd like to take over.
Yeah. Okay, sure. Okay, thanks, Aaron. Good morning, all. Welcome to day 2. So yesterday we focused a lot on HAFS going into operations and performance of HAFS, performance of other operational models. Today we will focus, starting with this session, on where we are headed. And keeping in mind as to the current challenges, and some of those were also discussed yesterday, we are seeking improvements in all different aspects of dynamical modeling. And this morning session will focus on something what we call HFIP real-time experiments, which have been running for more than a decade. And the idea behind these real-time experiments is precisely to test our innovations, test developments which were not complete, were not mature enough, or were not considered for operations the previous year, bring them in, and other modifications coming from our HFIP contributors, from our UFS partners, and design experiments. This is what was done for HWRF and HMON, and this is a legacy of HFIP, but a very important one. Frank took us through his journey and talked about computing and use of JET. And we still do that today. We're persisting with the same strategy. Of course, now we are trying to branch out and look into use of other systems because JET is getting old. And so we are trying to run, if not in real time, but near real time on other platforms, including cloud. So I talked a little bit about HURC yesterday, which was the first time we did real-time hurricanes experiments on the cloud, and that's hopefully just the beginning. So this session today is going to focus on all these real-time experiments. And we conduct these during the season, of course, and try and for sure address the storms which show up in the Atlantic. And if we have the capacity, we do it for the East Pacific as well. And whatever we learn from these experiments is then taken forward. It can be taken forward to operations if we are happy and those innovations are mature enough, or otherwise they're considered or reconsidered or reconfigured for subsequent years. And this has been a great way for us to kind of have our own test bed of real-time hurricane systems running during the season. All right, I think I've said enough. So let's get started. And I believe our first talk is by Zach and Shujin here on where we are with the current HAFS operational capability to set the stage for these real-time experiments. Thank you.
Good morning, everyone. My name is Dan Zhang, and I'm working at EMC Hurricane Modeling team. So today I'm going to talk about the HAFS initial operational capability, and I would basically will be focusing on the HAFS version 1 evaluations and performance in 2023 hurricane seasons, and I will touch upon the plans for the future HAFS development. And so basically, Xujing and I are presenting on behalf of UFS R20 hurricane application teams. Okay, so HAFS, as I mentioned, HAFS is a collaborative project. As usual, I would like to first acknowledge all the HAFS developers who are actually currently actively developing and contributing to the HAFS project. And we have already shown this slide several times. And without their contributions, I mean, HAFS version 1 would not be possible to be implemented in the operational in 2023. And also, as Avishal mentioned, a special thanks for the HFIP project, which provide JET reservation compute resources, this is actually part of the successful HAFS version 1 successful stories. So bottom line up front, and here are some key points that will be covered in my talk. And so 2023 has been a very busy but successful year for us. We reached a big milestone for hurricane modeling development, which is HAFS version 1 was implemented in operation on June 27th, 2023. And also we demonstrated with 3-year Richard spectrum 2020 to 2023, and that HAFS version 1 improved both track and intensity forecast compare relative to the legacy operational HWOF. And also in 23 hurricane seasons, in the operation, HAFS version 1 further proved its superior track and intensity forecast skills over HWOF. Improved the track forecast skills by like more than 15% after day 2, and intensity forecast skills by 10 to 20% after day 3 for all the storms in the NHC area of responsibility, which including North Atlantic and East Pacific basins. So here is a summary of the HAFS, the UFS HAFS project. HAFS is one of the UFS R2 project under the big umbrella UFS project. So the project is led by EMC and HRD. And of course, after like 4 years development, HAFS was implemented in operation in June 2023 this year. And also some of the major features of HAFS in the HAFS version 1 includes like UFS or FV3 based dynamic costs, atmospheric ocean wave coupling, and also convective allowing high resolution moving nests, and advanced inner core data simulation, and also the TC specific model and physics. So just as a reminder, we have implemented 2 configurations of HAFS in operations, HAFS A and HAFS B. Just to give you a quick summary. So basically, both configurations had the similar domain coverage and the same resolutions. And also we are using both configurations use the same data simulation algorithms, but with slightly different vortex initialization threshold for the warm start cycles. And also both HAFS configurations coupled with a two-way coupled with HICOM ocean models, but HAFS A also one-way coupled with WaveWatch 3. And the major difference between the 2 configurations is the model physics, and you will hear more talk in the later sessions, and the model physics. And we have slightly different model physics in the PBR and convection schemes, but the major difference is the microphysics. HAFS A uses GFDR microphysics, and HAFS B uses Thomson microphysics. Also, another difference is HAFS A is running for all global models, global tropical cyclones. HAFS B is exclusively running for the NHC area of responsibility. So this slide is showing you the HAFS version 1 performance in the 2023 hurricane seasons. This is earlier models comparing with other dynamic models, including HWOF, HMON, GFS, and COMS TCs. And this is for the 3 major global basins, and all the plots are in scale space relative to the climatology persistent forecasts. So yeah, so I just want to draw attention to the two lines, which is the purple line is the HAFS version, HAFS A, and the green line is HAFS B. So what you can see for the track forecast at North Atlantic and the East Pacific basins, you can see both HAFS A and B, the configurations are has the highest forecast skills. And for the West Pacific basins, actually GFS is the best, has the best forecast skills, and followed by HAFS A. Like HAFS A improved the track forecast over HWolf by like 80%. And for the intensity forecast at North Atlantic basins, as mentioned, like it's in yesterday several talks, and actually it's different stories. HWolf and HMON actually has the highest forecast skills, and both HAFS configurations are behind the HWolf and HMON in the Atlantic basins. I would have some explanations in the talk in the later several slides. But if you look at the East Pacific intensity forecast, actually both HAFS configuration are the top performers, top two winners, and also you can see, especially for the HAFS A, it's performing much better than other more dynamic models. And for the intensity at West Pacific, you can see HAFS is kind of comparable with the HWolf, and actually comps TC performance the best. So the question we are trying to answer is that how much forecast skill do we gain by running HAFS in operations relative to the legacy model HWolf in 2023 hurricane season? So, but for the combined NHC area of responsibility here, the stats, you can see that actually for the track forecast HAFS improved the track forecast go like 15% at day 2, and also 25% increasing up to at day 5, 25%. For the track for the intensity forecast, you can see, I mean, it's for the first 3 days, it's kind of have the same forecast skills, but after day 3, you will see like 10 to 20% improvement over HWolf for all storms at NHC area of responsibility. So I will switch gear to talk about a little about the challenges or issues we have, and because we have I mean, in general we have a very successful track forecast. So I will focusing on the intensity and focusing on 2 storms, Hurricane Lee at North Atlantic and Hurricane Otis at East Pacific basins. We identify 4 issues for the Hurricane Lee. So basically, in the right side, you can see the top two plots. You can see that even though HAFS A was able to predict the rapid intensifications, it either over predicted intensity or predicted the delayed rapid onset of rapid intensifications. So it's showing it's normally like a 12-hour delayed the RI onset. And another major issues we identified is that HAFS actually failed to predict the rapid weakening process. Actually, this is the big contributor to the total intensity stats for the 2023 year 2023. And also we noticed another issues is that the initial spin down issues, which is shown in the bottom left panels, left plots. And of course, everybody knows the HAFS missed basically all the rapid intensification events or cycles for Hurricane Otis. And actually, we have started looking at the issues, and I listed some of the possible causes, including the model physics may not, like for PBR schemes or convection schemes, may not be well presenting the real world, and also the resolutions may cause some issues for the Hurricane Otis, the small size intensification predictions like Hurricane Lee, Hurricane Otis, and also the initial high resolution data simulations. We are looking into it, and also the ocean, if there's any response, ocean response, if the ocean is responding correctly for these problems. So this slide actually show we did the verifications for the rapid intensification only. So this is just showing that basically all the Hurricane Lee contributes to these slides. Most, it's I guess like more than 80% of the rapid intensification are from Hurricane Lee. And you can see that the track forecast we are doing very is doing very well, but the intensity forecast both have configurations, HAFS configurations have actually over intensity, has larger errors compared to HWolf. So this is the important slide that we can see, just showing the Hurricane Lee is actually the outline. This slide is showing the intensity differences between HWolf and HMON. The vertical y-axis is the difference between HWolf and HMON, and the x-axis each individual storm IDs and the number of cycles. So basically, what you see here is that whenever you see the HAFS you see the positive values indicate the improvement, HAFS improvement over the HWolf, and the negative indicate the degradation, HAFS degradations. So the take-home message is that there's two take-home messages. One is that HAFS improved more storms in 2023 than degradations compared to HWolf. That's one important message. And another important message is Hurricane Lee is indeed the outlier. You can see basically just HAFS contributes most of the negative impact to the stats. So this slide actually, so the question is what does the stats would like if we exclude the Hurricane Lee? So this is the stats. You can see we maintain the advantage of track intensity, track forecast. You can see both HAFS have the highest forecast skills. But if you look at the intensity forecast, you can see without Hurricane Lee, HAFS intensity forecast skills are actually comparable or even better than HWolf. So that's the message I want to say. And also we did some of the outlier analysis for HAFS A and HAFS B. And so basically this is, which the slide is showing that the forecast errors as a function of cumulative percentage. And the top panel shows the track forecast errors, and the bottom panel shows the intensity forecast errors. So what we want to see is that the forecast, the smaller forecast, we want to see the smaller forecast errors that reach to the high cumulative. We consider that is as a good models. Which means if you compare the lines, we want the farther the lines are to the right, the better the forecast the model is. So basically, what let's go back. So the message here is HAFS A has less. Sorry, how do I go back?
The little red button there.
Okay, yeah, got it. Yeah. So the message here is HAFS B has less outliers than HAFS A in both track and intensity forecast. You can see HAFS B has and the line of HAFS B moved to the, has like right at the right side of the plots. But so this slide shows the same outliers, but for the East Pacific, the message is kind of different. You can see HAFS A actually has less outliers than HAFS B in both track and intensity forecast. So this is a three-way comparison for the same outlier analysis at 72 forecast hours. You can see, so the messages are the same. You can see the HWOF, which is the red line. You can see it's always, normally, in general, it's normally at left side of both HAFS B and HAFS A. So that's the message, so, which means that HWOF has a higher probability to produce a large track and intensity forecast. So this is a 4-year stats, which showing the 4-year stats for track and intensity forecast for all for NHC area for responsibility. Including 3-year retrospectrons and 1-year operational runs. So the messages are very clear. Look at the sample size of this, which is very large, and so the results are pretty clear and robust. You can see for the track forecast, HAFS improve the track forecast at all forecast lead time and like a greater than 10% after day 2. And for the intensity forecast, again, we improved HAFS A, or both HAFS improve the track intensity forecast at all forecast lead time again. But and also after day 3 or day 4, you can see like more than 10% improvement over HWOF. I just want to remind you, this is 4-year stats, so which is, we have a huge sample size. So again, moving forward, we are already looking for the HAFS version 2 development and upgrades. So here are some potential HAFS 2 upgrades, and some of the ideas has already been tested in the real-time 2023 real-time experiment. You will hear more in the later talk. For example, the HAFS A by Bing and HAFS B by Andy, and also Hinsuke will talk about MAM6 upgrades. So basically, in this slide, all the black items are common for both HAFS version 2, HAFS configurations for version 2 upgrades, including we are going to use the latest UFS, and we are going to improve the model efficiency and also the new capability in the workflow. And also for the data simulation, we have a lot to do. I mean, first we are going to simulate more high resolution observations, for example, AMV, high resolution and mesoscale, and also CONUS AMV data. And also we are trying to improve the data simulation by using the wave 0 data DA increments like HWOF, what we did for HWOF. And also we're probably, I mean, this the all scale ghost ABI radiation assimilation that's probably OU will deliver to us. And also we are trying to, I mean, if computer resource allow us, we are trying to do the cold start HAFS-based ensembles. So it will catch up the flow dependency error covariance background. And also another important upgrades we're going to do is we are adding hydromedial relocations in the vortex initializations, and also we are going to use upgraded GFDR trackers. And the red items is for HAFS A upgrades, which included we are trying to further increase the horizontal resolutions from 2 kilometers to 1.5 kilometers. And we are switching from GFDR microphysics to Thomson microphysics because, I mean, based on our test, it seems Thomson microphysics produced better results. And also we are going to transition MAM6 HICOM to MAM6 ocean coupling. And for HAFS B upgrades, basically we are going to focusing on the physics upgrades, including the PBR scheme tunings, and also switching from NOAA land surface model to NOAA MP schemes, and also we are going to do some improvement in the convection schemes, and in the HICON ocean coupling, we also going to tune the critical recharge numbers. I guess that's all I have. Thank you very much.
Okay, thank you, Zach. So we will have time at the end of the session for some discussion. So I would encourage everyone to not yet, to remember your questions or note them down, and we can discuss them at the end of the session, at the end of the talks. Our next presenter is Dr. Bin Lu, who is going to talk to us about one of the real-time experiment, HAFS 1.1a. And Ben, all yours.
All right, thank you. I think thanks for Avish's introduction. Also, Zach's presentation already set a very good stage for us moving forward. Basically, Zach talked about the operational HAFS A, HAFS B performance for the 2023 hurricane season. In the meantime, we do have several HFIP supported real-time experiments. We have HAFS A, 1.1a experiments. I'm going to talk about it starting right now. I think we have several other real-time experiments as well. But for my talk, I'm going to focus on the HAFS 1.1a configuration. As Zach mentioned, this configuration is going to focus on, based on the operation HAFS A configuration. And before I move forward, I want to thank my co-authors, collaborators here from EMC, from AOML, also from the UFS Hurricane application team, the whole team. I also want to give a shout out to the HFIP real-time project reservation, also for the jet element system support. Without those, we cannot run the real-time experiments smoothly. Actually, this hurricane season, I believe we ran the real-time experiment very smoothly. Okay, with that, I think this is basically for HAFS version 1.1a configuration. We ran real-time experiment for 2023 hurricane season. We ran actually all the 3 basins, including North Atlantic Basin, East Pacific Basin, and the West Pacific Basin. And I think I will not go through all the aspects here. I just highlighted a few things. For example, we are using high resolution. Zach already mentioned 1.8 kilometer resolution versus 2 kilometer resolution for the moving nest. And we are also developed and enabled the cloud variable relocation, one cycling. This is kind of a critical capability. We already wanted this for HWolf for many years, but right now we have it for HAFS, which is great. And we also turned on the simulation of high resolution ghost R AMV data. So these are additional data we have not been submitted in HWolf. I think even for HAFS version 1, we are just using as monitor mode, but for version 1.1a, we're trying to assimilate additional data. Another thing is microphysics. We talk about the Thompson microphysics instead of GFDL microphysics. Another very important aspect is Month-6 coupling. I think Hans' talk gonna cover the Month-6 coupling more. I'm gonna quickly go through it. Before we ran the real-time experiment, we actually kicked off a 2-year retrospective test with this configuration. So the stats is showing here, compare against operation HAFS A configuration. For the track, we got a pretty much neutral performance, but you can notice there are some noticeable intensity forecast performance after day 3. So before I jump into the real-time experiment results, I just want to highlight a few things. Like I mentioned, for the VI capability to relocate and cycling the cloud variables, I think these slides coming from Jianhong. You can notice there are some improvements in track, in intensity, like days 3, 4, 5. The best noticeable improvements is for the storm structure. You can notice with the cloud variable cycling, in the middle panel coming from the HAFS parallel A experiment initialization, On the right panel, you can see Doppler radar observation. You can see very realistic stone structure. You can see the double eye wall actually in this case. However, on the bottom left panel, that is without cloud over wall cycling, the stone structure basically totally missed the stone structure. So this is, I think, a very powerful, beneficial thing for us to include in the next version of HAFS. Oops. Another aspect is, as I mentioned, we are assimilating additional ghost R AMV data. This is actually for Hurricane Lee. I think Jin ran a few cycles for Hurricane Lee. The stats is only for like 17 cycles, but you can see we do find some tracking improvements for the earlier Fox Lee times. But I also want to point you to the intensity forecast. You can notice some very good intensity improvement at before day 2, basically. Several cycles highlighted here. You can see with their additional ghost R high resolution MV data, it actually surprised me a bit. It actually corrected the rapid intensification forecast phase. So the timing is much better than the control one. It also helped a few cycles of rapid replaying cycles, which also basically tell us by using additional AMV data, we are getting a probably better initial condition, helped us for, especially for this case, the intensity forecast. Another important aspect is the GFD, the Thompson microphysics scheme versus GFDL microphysics scheme. I think this is from Weigo. He did like 2-year retrospective test. I just want to draw your attention for the intensity improvement. You can see there are huge intensity improvements after about day 2. Also, helped is stone intensity bias. Vmax bias is better. Also, the radius for 34 knots wind are actually also get a better bias overall. For ocean coupling, as I mentioned, we are using MOM6 coupling this year, which is, I think, the first time, of course. And the overall impact for the track is actually very minor. It's almost the same. For the intensity, you can notice there are probably 2 to 5% of intensity improvements at the day 2, day 3 Fox Lee times, but not major, I would say. So again, Hans talk gonna talk about more about this. Then for the real-time power expander results, this is for the whole Hurricane 2023 hurricane season for all the low static storms, basically 2L to 21L. We started the real-time expander in August, but we did backfill all the storms since June. So this is basically the light blue line is the power layer HFC. You can see we got some additional improvements for track. You already remember Operation HFC, HFSP already did much better than other operation models in terms of track. So the power layer HFC got even better in terms of track. For the intensity, you can also notice we have some like 10 or even 20% improvements at the day 4, maybe 5% improvement at day 5. So these are also encouraging results moving forward for version 2. There are some also intensity bias improvements for Norganitan as well. And then for the next few slides, I'm gonna highlight a few storms or challenges. For even for the power layer HFC, we still have challenges. So this one is for Hurricane Idalia. Actually, the power layer HFC did a pretty good job in terms of the track forecast, especially before the landfall. For the intensity forecast, you might notice a few cycles of power layer HFC got over-intensified for Hurricane Idalia. I want to also draw your attention for the storm structure. Okay. Probably you can just notice, compare with the TDR data, actually the power layer HFC got a very good storm structure. So another storm is, of course, Hurricane Lee. We all know Operation HFC has been suffered. Power layer HFC has the same story, basically over-intensified for a few storms. And actually, all the models missed the rapid intensification phase. And another major issue is over-intensify for a lot of cycles. We did do several sensitivity experiments. Just tell you 2 facts here. we do have some experiments which can actually get pretty good results for Hurricane Lee. One is focused on the physics of the observation. The other one is focused on dynamics. So you can see the green line and orange line actually get very good results for Hurricane Lee. But I will tell you, those were not always good for other storms. For the sake of time, I'm going to skip the Hurricane Lee for the ocean coupling part and I think you can see in Hans' talk. Before the Andy, I also want to talk about Hurricane Felipe. We already mentioned HAFS A, HAFS B actually did a pretty good job in terms of track. For this storm, you can notice HWF is suffering. HAFS A is actually a little bit better. Probably HAFS A is even better. So in terms of intensity, you can also notice probably HAFS A got less cycles over intensified for this storm. I think with that, actually, you can also see this in the stats plot, and this is just one cycle highlights. Actually, all the three HAFS experiments or operation model did a better job for this specific cycle for Felipe. And one point I want to make is basically you can notice probably the reason is the HAFS model is doing a better storm-storm interaction, especially for this storm probably. That's something we probably need to dig into more in the future. And I believe this is my last slide. I just want to mention one fact here. This is combining the retrospective test and the real-time parallel experiments. The parallel HAFS A compared to operation HAFS A, you can see again for the 3-year for Atlantic Basin, we got a pretty much neutral impact for the track, but you can see about 5 to 10% improvement at day 5 for the track. Remember, we already got a very good track forecast for HAFS. And for the intensity, the 3-year sample also give us a better intensity forecast at the day 3, 4, 5 to 10% additional improvement, which will give us a very good position starting developing HAFS version 2 upgrades. I think that's all I have.
Thanks, Ben. Once again, folks, if you have questions, please jot them down. We'll discuss them at the end of the talks. Next is on HAFS B 1.1b. And I think Andy will be giving us the details about the performance for this experiment. Andy.
All right, well, good morning, everyone. Thank you for being here. Lots of interesting results so far. I'd like to echo what Ben said about lots of thanks to VJ and Wei and Ren and everyone at JET admin that worked hard to get that system get it in good shape for this season. We were able to have a lot of success, I think, thankfully, thanks to their efforts. And yeah, so I'm excited. I'll be talking about the HAFS 1.1b results. I'd like to thank my collaborators, Lou, Chunkai, and Wego. 3 of them were big helps in helping me run it, when I was out for hurricane research flights or other things. And of course, everyone at OML that helped this configuration. So the experimental version of HAFS B is sort of, one of the goals we're hoping to eventually get to is obviously improve the skill, but also increase the diversity with HAFS A. One of the big changes in HAFS, the experimental version I'll be talking about, is a change that we made in collaboration with Lisa Bingston and some of the work she's done to the scale-aware SAS convective scheme, this prognostic sigma or prognostic scale-aware closure. So it's kind of a new way of doing that, handling that scale awareness and hopefully getting better representation of the convection at different scales. So we have a couple other tweaks, including some changes to how we do the mass flux calculation in that TC-PBL option that Jiamin, Chin, and I have worked on. The hope was to improve wind radii forecasts and also some tweaks to HICOM to reduce mixing along the shelf. And this is something I did in collaboration with Lou. So we'll start with the Atlantic, the track verification. So on these plots, I think Jason showed some of them yesterday, but basically, you have the consistency metric from Sarah Ditchek's work. So dark green or green is better, dark green is even better, brown is degradation. So it's kind of a measure of how robust things are. So basically for the baseline for these runs, I used the operational HAFS B and then the experimental versions here in magenta. what you notice, the take home is that the experimental version shows improvement over HFSP and track skill, which is good because as was noted yesterday, we already had pretty good track skill from HAFS, both versions of HAFS, so we seem to be getting even better with that. Maybe thanks to how some of the large scale processes are being handled in the convection. If we look at a few of the individual TCs, Nigel and Franklin are kind of two that a few that stand out. So it wasn't just one case that was leading to all of this. For intensity, it's kind of a little bit more of a neutral or mixed bag. If you look at the overall, skill improvement, it's maybe like 2%. So, and in terms of the bias, there was a reduction of the high bias that we saw in operational HAFS-B. So that was encouraging. If you look at some of the individual cases, you kind of had more of a up and down, a little bit of a checkered look. For Philippe, which was one of the big problem cases, the experimental version did well, and also for Tammy, we saw a little bit less of a tendency for the HFX be the experimental version to want to RI, but there was some cases like Franklin where there was degradation. And in terms of radii, this is one area we're still kind of working on improving things. You can see that the experimental version of HAFS-A, which is in green here, was pretty different from the operational HAFS-A, but we didn't really see a whole lot of improvement, just very slight, probably not really significant in HFX-B for R34. And then kind of RMW is kind of a mixed bag, but kind of improving these outer wind radii in the Atlantic is something that we're still sort of trying to pin down with HAFS-B. For these specific, again, we saw even a little bit better track with the experimental version. In the magenta, kind of a larger improvement at longer lead times, but the sample was not huge. We're still kind of going back to fill in some of the very early season cases for that. One of the big ones was Lydia, which was kind of a tricky track case that a couple people talked about yesterday, how it sort of went out and then kind of came back. So the experimental version seemed to handle that pretty well. In terms of intensity in these specific, maybe a little bit more improvement here relative to the Atlantic, a lot of it at longer leads. And these specific, there tends, I think, to be a little bit more of a correlation between the track and the intensity errors because of some of the gradients in SST and other things you have out there. So we saw that big improvement in track for Lydia, and we also saw intensity improvement for there as well. And what's also interesting is that the radii issue we see in the Atlantic does not really show up in the Pacific. I don't know if that's just sort of an artifact of there's more recon, more observations in the Atlantic, but that's just we didn't see that same bias. But the experimental version was a little bit better. So I want to finish by looking at a few kind of cases that were both interesting for research and also challenging for some of the experimental for HAFS and the operational as well. So this is for Lee. You can see that both the experimental version and the operational version, and particularly for this cycle, the experimental version was the best at picking up the RI. Maybe a little bit of a timing bias, but it did a really good job of showing that intensification to Cat 5. But then the issue was that it just kept it strong and didn't really weaken it until much too late, if at all. And this is sort of a bias we saw across HAFS versions. So what I did is I looked at both our the operational experimental version we have here and compared it with the P3 observations. So these are some graphics that we host on our website, and I kind of combined them for this talk. And what you have is the precip and then the wind structure, 2 kilometers, some streamlines of winds at different levels. And then the vertical shear vector from ships, and it's calculated in the model, and OBS is also shown. It's a little bit hard to see here, but one big difference I noticed was that the model, both versions of HAFS were producing kind of a shear on the order of 10 to 13 knots, kind of more out of the west, whereas in observations, it was southwest and more like 17 knots. So maybe a little bit stronger shear in reality than what was being modeled, and certainly that's reflected in the structure. The P3 observations kind of showed, this was one of our first flights. This is one of the early flights in there, and by this point, the storm had already peaked and the core was getting eroded, more asymmetric, whereas HAFS was producing much too symmetric and strong of a core. So whether it was that missed shear or some other subtleties that were missed, we'll dig into more, but certainly the observations kind of tell us why. Philippe was another one. We saw this yesterday, big divergence in this case between a lot of the experimental and operational models. Both the operational and experimental HAFS-B versions did a good job keeping it weak, so that's good. If the experimental version had not done well with this case, we wouldn't have seen that in the stats, because this was kind of a unusual. You know, a 10-day sort of long tracked 40-knot storm is not something you see every year, and the stats are kind of biased by that. One thing that was interesting that I wanted to briefly show is kind of cool this year is since we had 4 operational hurricane models and the 2 experimental versions, you almost have like an ensemble of structure in a lot of these cases. So, and on our website, we have graphics for all of these. So if, for example, this is for that Philippe cycle, you have the 2 operational experimental HAFS-A versions, HAFS-B, and experimental, and then HWRF and HMON. And you can kind of see how, in HAFS-A and then HWRF and HMON, you got more of this sort of up shear wrapping. I don't have it here for the sake of time, but you had less vortex tilt. So if you go back, this was those are the ones that were too strong, whereas the ones that were weaker, not surprisingly, had much more asymmetry and tilt and things like that, which is consistent with what we saw in observation. So it was really nice to be able to compare the 2 versions there. Lastly is Hurricane Otis. This was one that has been noted. A lot of models missed. There was maybe like 12 or 18 hours before it peaked and then made landfall. A little bit of a picked on it, but really just very bad miss. And this is something we're going to be doing a lot of digging into to see what was going on. So just in conclusion, the experimental HAFS-B version incorporated several changes, mostly in physics. This prognostic sigma is kind of the big one. This is something I think that may eventually be in the GFS convective scheme. And as Ben talked about, maybe HAFS-A migrates towards using the Thompson microphysics as well. We're going to look at some of these convective scheme differences, this or some other ones to kind of keep that diversity. The intensity scale was kind of marginally better. There's some tuning and things we can do. Like I said, this change was originally designed for the MJO kind of large scale prediction, so probably needs to be optimized for hurricanes. And certainly, we saw cases like on looking at resolution, initialization, trying to figure out, is it storm scale, or like in the case of Lee, maybe it was a large scale shear issue that we missed, and looking to improve that as we look toward V2 next summer. So thanks, everyone.
Thanks, Andy. Okay, let's keep moving. So next up is Hansuk, and she'll be talking to us about MOM6 version of HAFS.
Okay. All right, so I counted oceanographers in this room. It's about 10% of the total. So let me see, you've been, looking at the chasing airs, but I'm gonna let you chasing a little bit, oceans, 10 times, viscous than air. So it's a little bit, slow, but, but I'm doing it. So MOM6, what I have done is for experimental demo for this project was that changing global MOM6 at low resolution. It's really practiced for climatology scale. So there was a lot of challenges to make it barotropic and add baroclinic and add resolving regional model MOM6. So this is one, sort of a taste of the regional high resolution MOM6. And then this bottom, okay, so the bottom boxes showing that HAFS MOM6 system, a little bit, introduced by Ben earlier. And then MOM6 is sitting here. So, previous version 1 HAFS is sitting, the HICOM sitting on this boxes. Okay, so we are using the same initial and boundary conditions coming from the RTOFs, which is based on HICOM, and then runs MOM6 for real-time configuration. So this is sort of a real-time exercise that they often, we use the real-time ocean product. So that's that's what it is. So, and then the ocean model configuration itself is a 112° and 55 vertical Z-star layers. And we do have a pulsing component coming from atmospheric side, including natural wave comes with 3 different bands, near RI, red and blue. So this one takes care of all the optical properties. So I think you saw this, plots from Ben's previous talk. I'm not going to go over, but let's take a look at the only skill parts and the bottom track on the left and the P maximum on the right side. And the blue color is the MOM6 coupled compared to operational HAFS 1, HAFS version 1A. So track skill is almost about the 15% better than in the HAFS version 1 at the 120 forecast lead time. And the pre-maximum scale is almost above 20% at the 96 forecast lead time. Okay, so EMC team has done the sort of working toward baseline with the MOM6, and they ran total almost 979 cases covering from 2021 to 2023, I believe. And then, so in other words, the purple line curve is in fact HICOM coupling, but everything else is the same, including FV3. So only differences between two curves, two different colors, is HICOM for purple and the MOM6 in teal colors. Okay, so this general statistics is similar to what stats we saw for pre-demo cases. So again, we do have a better simulation, better skills, but the longer lead time for track and then intensity. Okay, so everybody's talking about Lee, so I'm not exceptional either, so I have to look at it. So what's happening? And then in this V maximum plot in the curve here, I added 2 more lines with MOM6 with the EPBL mixing in a cyan or light blue, and the MOM6 with the KPP mixing in a teal color or darker blue shade. So we do have a different predictions for Hurricane Lee in this case, a little bit better with the KPP than EPBL, but it doesn't really take care of delayed RI and also in V maximum intensity forecast. Okay, so on the left side, what we have it's shown here is more like a track forecast against the best track in the black, and then we do have a little bit sail drones sitting in this right east of the one. I think it's about the valid time of 12Z on August, no, September 8th at the valid time. It's the closest one. So I'm going to pay a focus on this sail drone observations as well next. And this is heat content on the September 7th in 2023. And then bottom left one is coming from the analysis for from HICOM, which is based on encoder-driven field. And then on the right side, it's a NESDIS or ocean heat content products on here. So unit size in kilojoule per centimeter units per area. So, and notice that in the patterns in general, the model HICOM analysis field is a little bit weaker, and then compared to the analysis products on the right side. And then the coverage of the high heat content is pretty much stays in the Caribbean and the Gulf of Mexico. On the other hand, the NESDIS products have a little bit higher, almost, it's about above 100. It's sitting around the Lee focused track side. Okay. So this is sail drone in dark blues in a high density over here. Okay, temperature, and then salinity at bottom, and against all the forecast values, estimate values. So overall, no matter what, ocean components, model component, HICOM, MOM6 with the different mixing, they are general, the surface temperature is almost 0.5 or less, 0.2, 0.3 is cooler than what observed. during that intensifying period. And then salinity, surprisingly, there is a high salinity after the storm went by, but all the simulations is still under predicting it. Okay. Except that in a pre or during certain case, the salinity is pretty similar, and the even trend is very similar as a storm approaches to the location. Okay, now go to the more in details. So what? Oh, I'm sorry. So what I have shown on this plot is that upper layer mixing, measure with the Richardson gradient, Richardson number shown here, and the top panel is the buoyancy frequency n square numerator, and then and the middle one is the shear square. And then this takes care of the denominator of the Richardson gradient number. And then C is the Richardson number in shaded. Shaded area is where the mixing takes place higher. Okay. So notice that the n square in a very, very empty wide out places above almost 20-meter depth. That means that a lot of convection going on, which is unrealistic. But where the source coming from, in other words, density is much higher in the near upper 20 meters than below. So where the source of heat is. So, and the next one is the shear instability in the middle panel. Well, definitely we do have a lot of shears instability going on in the mixed layer depths, which is shown in the dark curve, black curve. And also there is a small spotted shear associated in the surface reinforcings. Okay. Now, compared to HICOM KPP mixing, that I'm sorry. Okay, so the negative n square parts above 20 meter, it's much smaller than MUM6, and also shear instability, and at the mixed layer depths, the magnitude is almost small. I mean, it's the same as a MUM6, but the shear associated with the wind, hurricane wind, not only magnitude, also that's the area of the shear instability is much larger than MUM6. And then bottom panel shows that in general shear is pretty much close to 20 or 10-meter depth, and then around along the track. This is the predicted track from the initial position all the way to 2,000 kilometers. Okay. So next, okay, so I've been looking at all the presentations, and then I haven't seen any details about the storm structures for leak cases. So I looked at it. I estimated azimuthal average temperature, potential temperature, and an estimated anomaly. Shown the shade is the anomaly temperature. Okay, and then control lines are the radial velocity, and the dashed line is the inflow, and then solid line is outflow. And the MUM6 on the left, and then HICOM on the right side as a function of this distance from the center all the way to height. Okay, so this is over the 24 hours integration. Okay, so I have noticed that in a very, very dark red existing almost throughout the column for HICOM. Okay, and yet MUM6 is not. Okay, so what I've been looking at all the time series of the entire cycle, and then this anomaly structure that is coming from the troposphere, stratosphere. Okay, so it's coming from upper layers and then intruding down to these locations. So it's called one core event going on, and then that might be driving this rapid intensification. Okay. And then this is the temperature anomaly as a function of distance and height at the each find the maximum temperature anomaly each 6-hourly simulations, and put it on one plot. 6 on the left, and then HICAM on the right side. And the lighter or white colors is much warmer, more than 16 degrees, and the blue is colder. So notice that in the HICAM, in fact, have a more number of higher temperature normally than MOM6, and also the extent of the altitude is pretty large. I mean, toward up. Okay. So conclusion. So high resolution eddy resolving MOM6 coupling is successful, seems to be working, but there are in a few items we have to iron out, like in a mixing, surface mixing, and then and the mixed layer depth, mixing at the mixed layer depth. Okay. And then we are moving forward, we are tuning parameters and the physics for eddy resolving MOM6, which include we can use EPP or EPBL or KPB mixing, and also diffusivity and the viscosity for MOM6. Turns out that it's very weak, so that's what I'm working on it, and then tuning for entire coupled HAFS system for 2024 versions. And the future planning is implementing Maroon Geodite for MOM6, and then merging MOM6 DA system to HAFS system for 2025 version. Thank you.
Thank you. Okay, we're going to transition. Avichal, you did a good job. Kept everybody on time. Will, thank you. So the next experiment is HREX 4, and Joe Olson and George Grell are online, and they're going to tell us about their experiment. George or Joe, go ahead.
Yeah, this is Joe. Thanks for the opportunity to present. I'd like to thank my co-authors here. You can advance to the next slide. Thanks. So our goal here is just to test alternative parameterizations within the GFS suite. So I'm really only talking about global runs here, 13 kilometers, medium range forecast here. The 3 runs we proposed were to replace the boundary layer scheme with MYN EDMF. Another one was to replace the SAS convection scheme with this new community convective cloud C3 scheme. I'll overview that a little bit later. And we're also going to do another run with replacing the non-aerosol aware version of Thompson with the aerosol aware version. I'll show a little bit of results and summarize in advance. Thanks. So we ran 2 7-day forecasts daily, initialized at 0 and 12 UTC off the GFS initial conditions, cold starts. We did do had to do a little bit of preparatory work to fit these suites into, or these schemes into the GFS suite. I'll overview a little bit of that later on. But this table just summarizes the departures from the version 17, which we're basically making changes from. So the C3 just changes the shallow and deep convection MYNN. Since it's somewhat mated to the aerosol aware version of Thompson as being developed with the, along with that, the RAP and the HER, we chose to run that with the Thompson aerosol aware scheme, and then but the Thompson experiment just changes the non-aerosol aware version to the aerosol aware version. You can advance. So here's just an important modification we made to the non-aerosol aware version. This is only to the non-aerosol, I'm sorry, only to the aerosol aware version of Thompson Eidhammer scheme, is the cloud water nucleation rates. Basically, they depend on a few things, but as the plot shows on the right, we're just showing how it varies for at 283 Kelvin for various vertical velocities. We know we have a high precipitation problem in the aerosol aware scheme, and this tiny little modification going from the blue curve to the orange curve, just increasing that nucleation rates, is really effective at patching this problem, as I'll show on the next slide. It basically, on the top is an example of overall the precipitation areas for a random case selected, just a single case, and the modified version is on the bottom. You can see a lot of areas of red over precipitation there on the right. So what this modification does is effectively increases the the number concentration of cloud water. And so there's more of them, and they're fighting for the same ambient moisture, so they don't grow as fast, they don't auto-convert into rain. And ultimately, this effectively reduces this precipitation problem. However, it radically changes the overall cloud cover. So a lot of changes had to be made to the MYNN to kind of regain compatibility with it, basically. So, and just in a nutshell here, basically just increasing the activity of the mass flux component is the most effective way to achieve this. If you go to the next slide, you can see that if you run with the original version of the MYNN with this modified version of Thompson, that's the blue curve compared to this updated version it worked on during WFIP, or sorry, during HFIP. You can see the big cold bias we had in the very beginning of HFIP in the tropics because of that excessive cloudiness, solely because of that. And it was greatly reduced, but this change didn't come in till September-ish, so we're still kind of running with a kind of a plagued version for the MYNN test here, but the Thompson test was, I think that's justified and made that specific experiment worth running. Go on to the next slide. We'll review kind of the C3. This is basically a unification project that basically takes the best of the GF, the Grell-Freitas, and the scale-aware SAS, and as well as other novel aspects that were spoken of, like in Andrew's talk, like the prognostic area fraction and closure. So things like that. But we thought we had a decent first draft of it at the beginning of HFIP to start with. But we did make some changes during it. We found that basically the shallow Q and the mid-level congestus were not properly coupled to the radiation. So there's some tuning implemented in August, as well as some rain evaporation taken from SAS. It was put in there in September. We stopped modifying everything by September because there's not enough time left. But you can see there's a big team involved in this, and a lot more are expected to contribute in the future. Go on to the next slide. We'll jump right to some of the results, and this is starting off with the Atlantic Basin. Overall, it looks like the C3 had the larger track errors, and GFS did pretty good in the Atlantic Basin, especially with the along track errors shown in the upper right, and where the MYNN did probably the best overall with the cross track errors on the lower right. Go on to the next slide. Still in the Atlantic Basin, but we're moving on to the intensity and then a little bit of the radius of maximum winds. Overall, a C3 was generally produced our strongest storms in general. And Thompson seems to have produced our weakest storms overall for this particular basin anyway. Radius of maximum winds, I see a lot of noise there. I don't see anyone really stick out. They're all high biased, so we're all producing a little bit too large of storms, but there's no one that's a clear advantage. Move on to the next slide and move to the East Pacific. It looks like this is where the C3 did a little bit better. I mean, especially in the longer range, it had the overall best track errors. GFS did also pretty good too. So the long track errors were the best by the C3 scheme, and then again the cross track errors were best with the MYNN. I'll go on to the next slide. We got the intensity. This one, strangely, the Thompson scheme seemed to perform the best overall at longer range forecasts. Otherwise, they're all kind of grouped together, all weak biased in general, as you kind of expect from the global runs with low resolution. But in general, the Thompson did the best, and the radius of maximum wind, Thompson also did the best there overall as well. Go on to the next slide. This is, Otis was mentioned in a few other presentations already, but this was really low predictability case. It had no one really shined. Not one specific product had a really good forecast track for this, and that was really essential for this rapid intensification you're seeing. Here on the right side, you see 3 different forecasts from October 10th through October 20th through the 21st. 3 different forecasts where, surprisingly, the C3, I mean, it kind of justifies their continued development during the project, because I think the C3 really started to shine a lot more near the end of this project, and I think it probably did the best overall with this really difficult track prediction, which allowed it to get some type of rapid intensification, although the timing was almost never right. But still, it was almost the only guidance it had that was producing anything over 80 knots. So it was just kind of I don't know, just anecdotal evidence that there was some improvement made throughout this project. The last slide, I think I just summarized. So this is, we just ran cold starts out to 7 days using different flavors of the GFS. And I think overall, the GFS, the controlled GFS still had the overall best track errors, especially in the Atlantic Basin, but the C3 did the best overall in the East Pac. I didn't show anything for West Pac because I found some irregularities in some of our statistics, and they weren't troubleshooted by last night, so I didn't add them. But anyway, no specific configurations stood out in a significant way for storm intensity or radius of maximum winds. They all had kind of similar biases. And I just want to note that all of our code modifications have been pushed to community repository now, so they're available for everyone. Thanks.
Thank you, Joe. And please hang around for discussion afterwards. Thank you.
Sure.
Our next speaker is Tim Marchuk. He's going to talk about HR 6, I think it is, or 5. HRX 5. Go ahead, Tim.
Morning, everyone. So I'm going to talk about the performance of our GFDL, T-Shield, and SHIELD models during the current season. So first of all, what are these models? T-Shield and SHIELD are both FE3-based models, similar to the HAFS models and GFS. On the right is our SHIELD configuration.
We're having an issue with remote where it's showing the next slide thing, so we got to change the way it's showing up on the screen.
We're having a little technical difficulty. We'll be ready in a few minutes, dear. For those online, it's a matter of getting the slides synced.
Yeah, I haven't been talking here.
We use the slide version. Let me just see that one slide.
You can do that.
No problem.
That's not him. All right, we'll just have to make it work. We're having issues with display, so
It just shows
And then
on there.
on the remote, it's showing the next slide view for some reason. We can't get it to go away right now. It's being very weird.
Okay.
All right, we're going to go ahead. Sorry about the slide issue.
Okay. All right. So, so SHIELD is a 13-kilometer global model. On the left is T-Shield. It also is a global model, but it has an additional tile, an additional high-resolution 3-kilometer nest that is placed over the Atlantic domain. And that allows for two-way interaction between the high-res nest and the global domain. Both models are cold started from the GFS with no additional DA, although T-Shield does have a vortex initialization that we borrowed from HAFS. One other note, there's no deep convection done in the Atlantic nest in T-shield. So I'll be talking about track intensity and real briefly on R34 with an emphasis on comparing against the operational HAFS models and GFS. Life cycle track plots are shown here. The colors simply indicate the age of the forecast. Brown forecasts are the oldest ones, green are the newest. In general, T-shield did fairly well for track, in particular for Idalia through landfall, for Lee. But problems here with making that sharp turn for Franklin, and then of course big problems for Philippe. Shield, very similar to T-shield, same problem areas with Franklin and Philippe, but again decent tracks for Idalia and Lee. So looking at track forecast errors by storm in the Atlantic, 72-hour on the left, 120-hour on the right. Same set of storms for both sets here. And basically, I picked the 6 storms that had the longest life cycles. So on the left for Shield and T-shield, the light blue and the blue, low errors for Lee. But what really stands out here are the larger errors for Philippe, about 220 nautical miles at 3 days. And then at 5 days, those errors for Shield and T-shield up around 450 nautical miles. But again, fairly low errors here for Lee and also for Tammy. Statistics for the global models only in the Atlantic Basin. As we saw a lot of yesterday, in magenta here, ECMWF was the leader in the Atlantic, followed behind by Shield in the light blue and UK Met in yellow and GFS in red. In the Western Pacific, on the left here, same story. ECMWF was the leader out ahead of the other 3 global models that are clustered together. Eastern Pacific, a little bit different story. Shield and GFS had smaller errors out ahead of ECMWF and UK Met. And 3 basin mean, again, the ECMWF was out in front of the 3 other models. So I added in the regional models here. This is late guidance. I wanted to add as many cases as possible, so I withheld the UK Met and ECMWF for this. And so you can be seeing here, HAFS B in the light green, as we've seen on others, had the lowest errors at 4 and 5 days. T-shield in dark blue matched the performance of HAFS A at 4 and 5 days. It's interesting, all 4 of these models, HAFS B, HAFS A, T-shield, Shield, all clustered together at 4 and 5 days with these lower errors. Final plot on track here. This is frequency of superior performance for T-shield. These FSP values are computed individually, head-to-head, between T-shield and each of the models listed, and I just put them all into this one plot. The values shown are the FSP values for T-shield in each head-to-head matchup, and so what you see is a gradual progression for the T-shield frequency of superior performance throughout the forecast period, gradually by 4 and 5 days becoming essentially positive for T-shield above that 50% line. For intensity in the Atlantic Basin, looking just at regional models here, mean errors on the left, bias on the right. So overall, HWRF had in the light purple here, had the smallest errors from 36 to 72 hours, with HMON close behind in the dark purple. Again, this is late guidance. HAFS B, smallest errors at 5 days. T-shield in the dark blue had generally larger intensity errors from 48 hours onward. And on the right here, the bias, a negative intensity bias that gradually grew positive by 4 and 5 days. So I stratified by initial intensity, with the reason being that we're using vortex initialization this year, and the cutoff for VI was 60 knots. So this is showing errors and bias for weak cases, less than 60 knots at the initial time. So T-shield errors were comparable to most other models at very early, very late times, but certainly larger than other models at 2 to 3 day lead time. HFIP had the largest errors at 5 days for this subset of weaker storms, and HAFS-B had the smallest errors at 4 to 5 days. For bias for weaker cases, T-Shield had a fairly strong negative bias at 2 to 4 day lead time. For the stronger cases, these are the ones where VI was used, initial intensity greater than or equal to 60 knots. T-Shield had a moderate negative intensity bias at up to day 1, and then eventually steadily grew into a positive bias for the remainder of the forecast period. And the errors also continue to grow for T-Shield with this subset. And one of the big problems here was intensification with RI. And so the 2 big problem cases for T-Shield were Franklin and Lee. And some of the, again, these are life cycle intensity plots. Some of the early forecasts in both storms missed the RI, and then the later forecasts were too late with that weakening, leading to that bias, positive bias late in the forecast period that I just showed. Okay, R34 biases, errors on the left and biases on the right. HAFS-A in dark green here had the lowest R34 errors from 2 through 5 days. The Shield R34 errors were larger than GFS errors from 2 to 4 days, and T-Shield was kind of right in the middle of the pack there. For the biases, T-Shield, Shield, and HAFS-B all had a fairly strong negative bias, R34 bias that kind of grew with lead time. It's interesting the difference here in the bias after day 1 between HAFS-A and HAFS-B. There's they kind of go different directions there. Okay, so to summarize, I won't go through all these. The main picture is that for track, for Shield, in particular T-Shield, did well for track, comparable to HAFS-A and close to HAFS-B. And then also for intensity, T-Shield struggled with intensity, in particular for rapid intensification. Can you go to that one slide?
There we go. Should be on.
Oh, perfect. Okay. Thank you. So last slide here, ongoing and future work. We'll be looking at comparison of TC Genesis performance between that nested regional T-Shield and the global T-Shield models, global Shield models. And then also Lin Zhang has been working on development of a C1536 Shield model, a 6.5 kilometer Shield model for global forecasts. And what's shown on the right here is animation of simulated radar reflectivity from work that Kung Gao has been doing on 125 meter T-Shield simulations. And so it's kind of nice to see a polygonal eyewall here and some of these finger-like cloud structures that are protruding just inside the eyewall. And also here's our Shield website if you want to see any of the real-time results from this year that Matt Marin keeps track of. So, all right, thanks for your attention. I'll be happy to take questions later. Thanks. Thank you.
Thank you, Tim. Very interesting, especially since George is looking to help us go to sub-kilometer, so he's very interested in that. Our last talk before discussion is going to be by Raj Panda and Jai. Jai is going to be presenting, looking at the cloud HAFS ensemble results. Jai.
Thank you, Frank. So yesterday, Frank gave a good review for first year HFIP. So we built the jet, right? We bought lots of chips for jet machine. But the previous year, this funding has been cut. So now, we're trying to explore other capacity. So we have the AWS cloud, we have Google Cloud, and also we have Microsoft Cloud. So today I'm going to talk about the first real-time run in the AWS cloud. First, I need to thanks to my co-author here. We have different people from like EMC Hurricane team, Fireworks, HFIP management team, and also lower cloud funding this project. So make this happen. So we start to run the project in mid of August. So currently it's still running, okay? So the outline here, so the first thing we want to know and tell you why we do this. So, and then we tell the what's configuration for HAFS symbol, and also what are the products provided by this focus system, and then we talk about the relocation for the almost the whole hurricane season, and we also run some storms for the 31 members against 21 members. So the last is I'm going to talk about the challenges and the configuration for next hurricane season. So we just showed this yesterday. So I quote a few hurricane fighter here. So the first is Mike from NHC. So lack of a dynamic regional hurricane model and symbol systems that can represent intensity and structure. So the second also from Wallace NHC. So we need to deal with the hazardous, so how we produce a better hazard products, including like the wind, the wave, storm surge, etc. So we need a mesoscale NWM model and symbol. Okay. So the other one is from the Matt. So GWC. So he mentioned, so we need a skillful, okay. Here, skill is the keyword here. So we need a skillful high resolution symbol to predict the T intensity and structure. So turning operation, so the framework, so provided the 11 member for co-amortization symbol. So, but with the NOAA, so far we have nothing yet, so in operation. So we have a big demand or request. So here, so we're here to fulfill the gap through the AWS cloud. So here's the configuration that we run the system with one. With one domain that's ESD grade 6 kilometer, low moving, and I'm not going to go too much for this detail for the model part. So the most important one, so for this hurricane season, we run a couple with HICOM. It's not a MOM6. So MOM6 the proposed for next year, next hurricane season. So for the ensemble configuration, we include the stochastic physics, SPPT, SCAP, and SHARP. So the initial bound condition come from the half degree GEFS script to data, and also with ocean initialization from our talks. So we run 4 cycles per day, and so in AWS clouds, it's around 6 loads per focus job. Okay, so that's the configuration. So here's the Sans Raj provided some slide for the how he helped to port the code to AWS cloud so we can run the system. So I want to point here is that we have the data over here. So in the AWS cloud, so anybody can get it. So if you need help, just send me an email. So we provided the group file provided like a 3D or timing or 4D or even probability will have 5D, right? 5-dimensional data set. So to handle the probability of the hurricane forecast. So then I'm going to talk about we have the system running in AWS cloud. So we almost deliver every cycle on time. So that's quite stable. So EMC has a website to produce the real-time product. The first one is here show you the August 28th 00Z. So this is for Hurricane Idania. This is the track. Look at the track. So the envelope track envelope cover the base track very well. So here's the maximum wind, and the lower panel show the P minimum signal pressure. So look at the I mean, the max wind speed and the civil pressure fully covered the observations. So another product, so see, this one is a very good one. So we provided the RI probability guidance. So this is from the August 28th, 0 So the horizontal is the timing, linear hour, and the 24 hours intensity change. Look at the red color is a warning. So before landfall, so the hurricane Idalia expected to intensify to category 3 and 4. So this is, we think, is a good guidance for the RI forecast. So, okay, this one, we also produce the wind speed probability. So here I'll only show the 34 knots. So we also have the 50 knots, 64 knots. So look at so yeah, this is for day 1 and day 2 and day 3 and day 4 and 5, and the whole life cycle 5 days. So I was trying to find the service wind analysis to compare this from the WP website. I didn't find it. Okay, so but for the precipitation here, I did find one. So we here show the precipitation probability greater than 1 inch. So that's day 1 and 2 and 3. So for the day 3, you can see that the pattern, the probability, it's matched. Here's show the CCPA most come from the stage 4 data set. So along the East Coast, there were heavy rain, so like the color, the green above those bright color. So the pattern, so the day 3 and this day 3 match very well for the precision. So here, so last year, so WPC, okay, actual meeting, okay, give a talk. I heard it, so they never use the HAFS models for their like presentation guidance. So we hope they can, use our products, help to carry their focus. So we have more products like the structure, the size. So please go to the website. We have real-time website that provide all the products. So if you have any question, so you can ask me and Jack and Weibo. Okay, anyone can answer you. Okay. Then we run the system. We want to know how the system perform. The first thing against the global model as our HAFS system built from the initial environment come from the GFS. So we need to compare with the GFS and also the Urban Center. So the performance. So this shows the intensity error, and the HAFS is we consider this yellow. Okay, yellow against the red GFS, and this for the E7WF. So I pull out the Urban Center, the 9 kilometer, the track data. So remember, our HAFS symbol is 6 kilometers. So it's only a little difference. Here's the EC in symbol already run 9 kilometers. So we try to figure out what's the difference, how the program. Okay. So the error. So the first few days, like 3 days. So we reduce the errors, right? It's a significant reduce the errors, and also look at the bias, the GFS and the Urban Center bias. So just reduce by 10 knots. So it's for intensity is a big win. Okay, but unluckily for the track. Okay, so the track yesterday, so NHC already showed the EC did pretty well for the Atlantic storm. We show here too. Okay, so for the track. So this is the HAFS against the GFS. The bottom one shows against the E7. So the HAFS symbol for track is not good for this season. So we want to figure out what's going on. So actually, I track most, every cycle from the website. So we find out that the Hurricane Philip, so it's a nightmare for HAFS symbol. Also is headed storm for NHC forecaster. So this is for only one storm verification. So look at the track error. So this against the GFS. So the HAFS symbol just degrade a lot for the track error. So the long track bias is not a big deal. It's around the 40 to 60. But look at the cross track bias. For the 5 days, we got the 300 to 350 nautical miles. And for the one single, I'll show you that's the right cross bias that show one focus. So yeah, we'll have to deal with this challenge storm for track. That's for Philip. So Philip will interact with the RENA, so the model is not handling well for this storm. So now we move to as the HAFS symbol is built from the HAFS A version 1, right? So we also want to know how this intensity performance against our operational HAFS A. So here I show you the errors. So the yellow is the HAFS symbol mean, and the red is the black is the HAFS A. So look at it. Except the first 24 hours, so all the rest, the linear hours, they ensemble predicted well. Lower or better than the smaller or better than the original HAFS A for the check. So for the bias, we figure out the problem here now. So as the HAFS symbol currently, our initial condition come from the GFS. We don't have the water ionization or TC relocation and the DA, so in the system. So that's why we have the initial need a bigger bias until the 460 hours. So the coming years, so if we can remove those bias, we're going to reach our dream bias level. So that's for the HAFS A. So we also run for some storms like Idania, we run a 31 member. We want to know whether the 31 member is better than the 21 member. So here I'm going to show you a few slides. So generally the 31 member can produce the better PDF and the spread. So this is for the chart for the one cycle, August 28th, 2023. There is the. So this is for the city. Okay, sorry about. Wow. Yeah, so this is for the city pressure and wind speed. So they have a better coverage for the observation. So we already talked about Philip for the track. So we also have another problem for the stronger storm. So here for the hurricane storm knee. So even the ensemble system produce very good. Yeah, it is very good track forecast, but for the intensity. So from the beginning, as we grab the initial condition from the GFS HFIP data, so the initial intensity is too weak compared to the observation. So even we produce the RI, but this RI is, a little bit far away from the observation RI. So that's another one we want to do for the next year to add the water ionization. Okay, here. So we have another ensemble system I already mentioned in the motivation. So here are thanks John and also Jim provided their HAFS and co-amps and symbol 21 member data. So then I can compare it. So for the track error, so the yellow is the HAFS and symbol, and the red is the co-amp TC and symbol. So looks like the co-amps TC and symbol did better for the track intensity forecast, and for the track is a very little difference. So again, we see this negative bias for the HAFS symbol from the beginning. So as we don't have the water initialization, so we're going to figure out this later. So the co-amps different symbol developed maybe start from 2014. It's around 10 years ago. So it's a well. So this almost my last. Okay. So we also compare the arrow, track arrow, and intensity arrow and spread. So both the two systems. So the dash is the dash line for the spread and also the solid line for the arrows. So the blue for the co-amps and the TC and symbol, and the red for the HAFS and symbol. So both systems under dispersed for the track intensity. So okay, so this is my final slide. So okay, so there are a few things as I will show from the previous slide to figure out some problem. So for the Philip and the Hurricane Lee, so the first one is the initial condition of the 20-member HAFS and symbol are taken from the GFS 30-member initial data. So there's a low rescission process for the current version. Either we run 30-member or we do the rescission process to remove the symbol mean bias. So that's the first one. The second one is I will mention it for the initial gain come from the GFS half degree. So the storm period week. So for this year, 2023 housing for the weak storm, the housing did very well. So only for those strong storm will have some challenges. So we may need a TC, location, VI, and DA to make an initial intensity closer to the observation, which will help them remove the negative intensity bias for housing symbol. So if we continue to run the 20-member for the housing symbol, we will adjust the stochastic parameter to make it more dispersive. So that's all I have. Yeah, thank you.
Thank you, Jai. Please wait for questions. We're in the discussion point here. We got about 15 minutes. Open the questions for the speakers. Jim.
Just a question regarding Otis to everybody. It sort of looks like the model storm feels the land before the real storm did. There's a possibility. Is anybody running an experiment where you just remove the land from the simulation and rerun and see whether that's the case or not?
That's an interesting suggestion. We haven't done that one in particular yet. We're doing a few different things, like looking at, trying to go down to really high resolution, see if that makes any difference. Running some of that ensemble configuration that was just talked about, to see if any members even got close. But that's an interesting idea, because my hunch is that it was probably atmospheric, because if you look, a lot of the forecasts even a day or two out had really bad tracks even before they got close to the land. So I think there was something that was missed. Maybe it was a easterly shear or just something very poor in the GFS initial short-term fields is kind of my hunch. But that is an interesting idea, because certainly terrain can play a big role there.
Yeah, I just want to respond to questions. I think that's probably good ideas, but I guess the main reason that we cannot produce the rapid intensification for the audits probably the resolutions. Maybe it's smaller, it's small size, and we probably need to increase the model resolution. That's probably the main reason. Yeah. Yes. But the size is pretty small compared to other stuff.
Just a comment on this, Jim. Thanks for removing land. We did this in Katrina when we started with the HFIP system itself, which if he's here, we did these. The problem with all these experiments, if you remove land, is the synoptic features that are corresponding to the environment, they get changed. So you go into another problem wherein tracks may get very, very different. So that's where the issue is in removing certain things, basically.
Frank? I wanted to go back to a question that was in the chat from earlier during one of the talks.
Okay, we have a question from the online. Zujin, did you want to respond to
before I
that before we go?
Yeah.
Okay, let him
So-
respond first.
No problem.
One of the framework we try to do is the idealized framework so that we can do process by process to, identify what is the main reason to that. Then we come to an operational model. Because it's so complicated right now, you mixed everything together, you cannot identify what is the single specific factor to impact the, this particular storm. Yeah, we talk more.
The question in the chat from earlier was from Philippe. He asked stated that he was curious on how, quotes, similar HAFS A and B will be if they're both using the same microphysics next year with the shift to Thompson. I figured, John, I figured you'd be a good one to respond.
Yes, actually, yes, that's we are also trying to figure out how do we diverse the model. So with HAFS, actually for HAFS A, we are actually considering it, but not only in the Thompson microphysics. We are waiting for the GFDR microphysics to be upgraded to version 3. Currently, it's using GFDR microphysics version 1, and there's also a chance that we are going to use GFDR microphysics in HAFS version 1, HAFS A version 2. But I mean, it depends on how the development the GFDR microphysics is. And another diversity we are considering is that currently we are coupling the different ocean models, and we are trying to use different convection schemes. I mean, we actually tried several different convection schemes, but I mean, Andy is trying to do like prognostic convection schemes. And another difference even though we are using the same Thompson microphysics, we may try different flavors, like to try to use aerosol aware microphysics. One uses aerosol aware Thompson schemes, and the other one do not. Yeah, that's right. Yeah.
Yeah, it's related too. I want to flip that question around and ask any forecasters or anyone from Forecasting Center in the room. I mean, did HAFS A and B provide the diversity you were looking for this year? And as we go forward, I saw some results that removing HWRF and HMON, the consensus, I guess, got better. But that aside, forecast to forecast, is the diversity something that is useful for the forecasters?
I'm looking around the room. I might be the one who issued the most forecasts from NHC in the room. So with the caveat that I don't write as many advisories as the hurricane specialists, I think that the unit is more comfortable having the diversity of 4 models than they are just having HAFS. I think maybe the most obvious example, and it's unfair to pick on it like this, but in Lee, both the HAFS models were off the chart with intensity. Different specifics in the forecast from run to run and all that, but they're both going to 160, 170, I think for a cycle or 280 knots. Whereas HMON and HWRF had strong hurricanes, but not quite like that. And I think that having the extra diversity of the other 2 models definitely helps the forecasters right now.
We have a hand raised from Jamie Rome online. Jamie, go ahead.
Yeah, I was going to attempt to answer the question. Great question, Gus. It requires a bit of a nuanced response, though. 2 members is better than 1, and 3 members is better than 2. So obviously, yes, it contributes positively to the forecast process, but it's not sampling the full spectrum of forecast uncertainty, which is why the HAFS ensemble approach under development now is the ultimate long-term hope and goal. Is that kind of what you're looking for?
I think it was, that was good. And Philippe also responded online, Jamie, so thank you.
I also want to point to a question that just came in from, I believe it was from Buck Sampson. It's getting cut off on the screen for me right at the moment, but is the HAFS ensemble available for JTWC basins? And I know the answer to that, actually. I didn't need to look at the room. The answer is no.
Yeah, this is Wallace from the Hurricane Center. So going back to the HAFS ensemble, number one, I think this is really, really important. Jamie just said it. So thanks to EMC for running this experimentally and getting it started. Long term, yesterday we were talking about HFIP goals and kind of where we're headed, and people were talking about some structural variables. Maybe we want to start verifying. I'd like to make the pitch to start looking at very, very fine details of how the ensemble systems are performing. So maybe setting a baseline, looking at, spread skill metrics. How are these systems comparing against some kind of baseline, like the operational wind speed probabilities for things like the 34 knot wind swath, 64 knot wind swath. I think as a community, we could set those goals and set the baselines and let all of the teams work toward some objective, because these systems are going to be the foundation for our risk communication.
Yeah, go ahead, Pablo.
Certainly, Pablo, NEC, certainly echo what I just said. I had a question though, ensemble. Do you guys have a sense or confidence, however you want to think of it, that you can largely correct for the under-dispersiveness by tweaking either the initialization, data simulation, the physics, versus just increasing the number of ensembles, the members that go into it? What is your confidence that you can strike a balance there, or there's no way to avoid in the future having to go with greater number of members?
We have aspiration. This was our first foray, Pablo, and we actually didn't even have plans for it, but thanks to some valiant efforts and coordination between multiple parts of NOAA, it happened. So this is just our first foray. And as Jai, I think on his last slide, listed some of the challenges, which include some of the issues you are raising. Those are definitely in our plans, absolutely. And we want to continue with ensemble testing in parallel to what we are going to do for operations. So this is just the start. And we plan to look at all those issues. And addressing all of that, it's difficult to put a timeline or anything like that. But this is an opportunity for us to, and especially with the support and general consensus here, that this is the direction we need to pursue. We will be looking at a number of things.
Right. So it was addressed a little bit by the talks on what data is being assimilated here. And both our marine forecasters and our hurricane forecasters are starting to get inundated with these experimental new observations, whether it's ultra high res scatterometer, SMAP, SMOS, synthetic aperture radar, Cygnus. Are any of the HAFS models using any of those experimental data sets, especially keeping in mind that in the Atlantic, we don't have recon 70% of the time. And in the East Pac, we don't have recon 95% of the time. So these remote sensed opportunities really could play a big role in the future.
We have an afternoon session dedicated to DA, Chris. So what we are using right now and what we plan to use in the near future and long-term future will be part of that session, part of those discussions. In general, yes, we are trying to use more and more observations and bring them in. But of course, there are both science and technical challenges. For us to use the data has to be made available to us in real time, and it has to be available to us in a designated operational, from a designated operational server, ideally on GTS. There are other ways also we can get the data in, but those mechanisms, those pathways have to be put in place for any new observations. But that said, we are always looking for additional observations. And I mean, Darrell, maybe if you want to address that, you can, but we have a whole session dedicated to that later today.
I just want to add to what Avishal said. The back half of the afternoon has a session on presentations related to DA, and then we have an hour discussion on DA overall challenges, et cetera, that Darrell and Jason will be running. I know Jamie wanted to respond. Go ahead, Jamie.
I just wanted to build on what Avishal was saying and provide some context. He and I were able to squeeze out some money in the disaster supplemental to commence some of these experiments. And there's a lot unknown. I mean, this is a new frontier that's probably going to take many, many years to find the optimal number of ensemble perturbations that balances getting the full spectrum of uncertainty while not driving the computation costs through the roof. Whether it's full ensemble members or data mining or synthetic type approaches, it remains to be seen. But I think based off what we're hearing here, the community recognizes the importance of this. And so I would stress upon the community to advocate for this type of approach, because Avishal is going to need that support, especially financially. The disaster supplemental is not permanent. I mean, it largely ends late 24, early 25, depending on how people are spending. So we'll need some sort of augmentation of funding on the back end of that to keep this going and really allow him to build into the future. So all great questions, but Avishal is also working with a very little bit of seed money to explore this space.
So I have a question before we end. A couple of meetings ago, we talked about R34 definitions. And I know, Tim, you modified your tracker to try and be more consistent with the way operations does R34. Have we come to a conclusion that they're similar? Would somebody from the operational community look at a model field from HAFS and define the R34 the same way the tracker does? Because we always see a bias. And it's not clear why there is a bias. Is it a model issue? Is it the way we define R34? If we're going to develop these statistics, we need to have some consistency, because our baseline is the ops, which we know are, have uncertainty as well. And so we need to start quantifying these things and characterizing them so that we understand we're talking about apples and apples.
I'd like to cut you off there, Frank. I'm sorry. Can we just make that as a challenge to people to think about, only because we're
challenge from 2 years ago? And I still want to keep it on the table.
I completely understand. Yeah, go ahead.
Yeah, actually, this is response to several questions previously about the HAFS ensembles. And regarding the uncertainties and perturbations, and because this is the first version of HAFS-based ensembles, we do not have to develop all the perturbation method. This is the configurations of this ensemble versions is totally different from what we did in the past for the HFIP ensembles. So the perturbations, we are just used whatever available to us for the stochastic model physics. Unlike in the HFIP perturbation, we are perturbing drag coefficients and convection triggers, and also surface SSTs. So all the perturbations and uncertainties we are putting in HAFS based ensemble are totally different from HFIP.
All right. Thank you, Zach. All right. With that, we're going to have to take our break. I do want to say a couple things before we go to the break. Molly wanted me to announce that the Vice Marks HRD Director position announcement, since Frank mentioned it yesterday right as we were leaving, will be going online on December 1st. So if you are interested, please look into that. I also wanted to mention that we'll be doing our group photo right after lunch. So those of you online, please come at the beginning, just before our afternoon session start, and turn your cameras on so we can all get in front of the screen and get everyone together. That said, we'll see you back here at 11:15. So it's more like a 12-minute break. Thank you.